Welcome to FSATC's Physics 131 workshop. We're going to be going over some basic Physics 131 concepts. So we're going to be going over the presenters, objectives, electric charge, electric field and fields and forces, electric flux, and charges on conductors. Now, this is going to be a basic conceptual overview. We're not going to be jumping into any problems today. We're just going to be going over the theoretical part of all these topics. This is the Instagram and Facebook QR code. I'll let this be here for a minute. Go ahead and grab that if you guys want to know more about the recordings or more about the tutoring center, or stay updated on our future workshops. I'll give you guys a second. Let's get started. So if you guys can sign into the workshop, oh my god. You know what? I'm just going to drop this link in the chat for you guys, so it's easier for you guys to sign in to the workshop. So if you guys can go ahead and sign in while I go over the topics again. So my name is Shreyas. I'm a junior in biomedical engineering, and I'm part of the special programs team.
I'm Aishwarya Ranjan. I'm a computer systems engineering major in my junior year, and I'm also with the special programs team.
And today's learning objectives, like I said earlier, are electric charge, electric fields and forces, electric flux, and charges. Oh, never mind. Charges on conductors isn't a part of this, but we're going to be going through these three topics. I just remembered. My bad. So let's get started with electric charge. So first off, we're going to go over the classification of materials. Electrons surround the nucleus in a cloud of negative charge, and this cloud has a definite structure, which we classify materials according to. So you guys already probably know this. There's three basic kinds of materials: conductors, insulators, and semiconductors. So conductors are materials in which the electrons are free, and these free electrons enable these materials to conduct charges and heat. So for example, metals like copper, aluminum, silver, they're all conductors. Insulators are where the electrons are bound to the atoms and they don't move around as freely. So charge flows with great difficulty, if it does even flow. And examples of insulators are glass, rubber, wood, and fur. And semiconductors have electrical properties that are somewhere between insulators and conductors, like silicon and germanium. Now, you probably, like in day-to-day life, you see these used in computer components and like CPUs and stuff like that. So let's go over charging by friction real quick. So the frictional charging process results in a transfer of electrons between two objects. And as a result of the electron transfer, the two objects become charged with opposite charges. So for example, rubbing a glass rod against silk charges both the glass rod and silk, where the glass rod becomes positively charged and the silk becomes negatively charged. And we're going to go over the principle of conservation of electric charge. So electric charge is always conserved in an isolated system. This means that charge cannot be created, and that the sum of all electric charges in a closed system must be constant. So if the system is closed, electric charges can't just disappear or appear out of thin air. Essentially what it's saying is that they can't be created or destroyed, and they're just conserved. And when there is a transfer of electrical charge, only electrons are transferred from one object to another, not protons. So whenever we talk about a transfer of electric charge, we're always referring to the transfer of electrons, never the transfer of protons. Now, let's go over electric fields and forces. So the unit of charge is the coulomb, which is denoted by a capital C. And 1 coulomb is a large amount of charge. So 1 coulomb, so what the charge on one electron is 1.6 times 10 to the negative 19th coulombs. So that just shows you how large of a charge 1 coulomb is. So for this reason, we quantize energy. So electric charge Q is quantized. And basically when we say it's quantized, it means it comes in discrete packets, where Q is equal to plus minus N multiplied by E, where N is an integer, and E is the fundamental unit of charge. So basically what we're saying is that electric charge Q only comes in multiples of this value here, E, which is also right here. Now this is the charge on an electron, or if it's negative, it's the charge on an electron. If it's positive, it's the charge on the proton. So what we're saying is that electric charge Q can only come in multiples of that charge. And the term point charge refers to a particle of infinitesimal small size that carries an electric charge. So it's just a very small particle that possesses an electric charge, positive or negative electric charge. The electrical behavior of protons and electrons is described by modeling them as point charges. So whenever we refer to electrons or protons, we just call them a point charge because it's easier to visualize them in that situation. It's also easier to understand the concept of quantized energy when we depict them as a point charge instead of depicting them as an electron or as a proton. So let's go over electric forces real quick. So force is equal to the product of two charges times a constant over the distance squared. So the force between particle 1 and particle 2 will be equal to K multiplied by Q1 multiplied by Q2, and the whole thing is divided by R squared. So Q1 and Q2 are the product of our two charges. K is our constant, and R is the distance between the two charges squared. Now, this formula right here only gives us the magnitude of the force, but forces are vector in nature. That means they have a direction. So here, this is virtually the same formula as we had up here, except we're multiplying the force with this vector right here, R12. Now, this is just a unit vector that indicates the direction from particle 1 to particle 2. So it doesn't actually affect this value right here, but it just gives it a direction. Let's go over Coulomb's law real quick. So the K we just saw previously, is called Coulomb's constant, and that K is equal to 8.99 times 10 to the 9th Newton meters squared divided by Coulomb squared. And keep in mind when we're calculating electric force, that electric force is a conservative force. So work done by electric force is independent of the path taken. So this is a standard principle that you guys have seen in Physics 1 quite a bit. The same principles are applicable here in Physics 2 when we're talking about electric charges and electric fields, forces, stuff like that. And the charge of a proton or an electron is the smallest unit of charge, excluding quarks. You will not be dealing with quarks in this class, so this is the smallest charge that you will need to use for calculations. And we already went over this, where E is equal to 1.6 multiplied by 10 to the negative 19th coulombs. Now, we've worked out a model for a two-charge system, but if a third charge is added to the system, we can use the principle of superposition to obtain the net vectorial sum. So if there's three particles and you want to calculate the force on particle 1, for example, you'd calculate the force on particle 1 and the force applied by particle 2 onto 1 and 3 onto 1, and you would just take the vector sum of those two forces. Now, let's go over electric field. So the electric field is defined as the electric force on a test charge divided by the test charge. A source charge creates an electric field in the region of space around it. So imagine a point charge, like a proton or an electron, that's just going to create an electric field around it. And when a test charge enters this electric field, an electric force acts on it. So when a test charge enters the electric field, it essentially interacts with the electric field. And due to the other point charge that is creating the electric field, an electric force will act on the test particle. And the unit of electric field is newtons per coulomb. So it's force per charge, basically. And the electric field is also a vector quantity. So when we're denoting electric field, just like force due to electric force, we're going to denote it using a vector, basically what direction the force is acting on it. And even in this case, it's going to be a unit vector, because if we don't use a unit vector, it may influence the value of the magnitude of the force. So that is why we use unit vectors for this. So let's talk about the electric field of a point charge. Now, these are just some important pointers to keep in mind when you're dealing with a problem that asks you for the electric field of a point charge. So the field is produced by a positive point. The field produced by a positive charge points away from the charge. So essentially, if it's a positive point charge, your electric field is going to be going away from it. It's going outwards. Essentially, it's like, imagine it as it's radiating electric field, basically. And the field produced by a negative point charge points toward the charge. So it's all condensing towards the charge. Just imagine it's being sucked in by the charge. And the field produced by a source charge or charge distribution is independent of any charge, any test charge. So basically what this is saying is that if a point charge is creating an electrical field, the electrical field will not be influenced by any other particles present in this electrical field. Essentially, it's saying it's independent of the other charges present in that same electric field. The only charge that matters is the point charge that is creating the electric field. And like it says right here, the electric field is a property of the source charge. So when you're trying to calculate electric field, you can disregard at times all of the other particles present in the electric field, because you only need to deal with the source charge. And the test charge only serves as a detector of the field. So the only reason we really place the test charge there, or for calculations, is to understand the electric field and what it is. Because otherwise it's hard for us to gauge what exactly the electric field is. We need a point charge and see how much force acts on it to understand the strength of the electric field. And like I said earlier, the field is present whether the test charge is there or not. It's just when we're working on it mathematically, it's hard to prove that the field is there without a test charge. And a point charge Q produces an electric field at all points in space. So regardless of where the point charge Q is placed in space, it will produce an electric field. And this field, the strength of this field decreases with increasing distance. So the further away you get from the point charge, the less strong the electric force is. I like to think of it the same way we think of gravity. The farther away you get from the Earth, for example, the less gravity you experience from the Earth. Now, electric field is defined as a property of space in which an object experiences force. So the electric field is just present in space, and any object present within the electric field will experience, any charged object within the electric field will experience a force. Like I used the gravitational analogy earlier. So for dealing with gravitational field, a mass m experiences a force, but if we're dealing with an electric field, a charge q experiences a force. So honestly, the best way to go about thinking about electric fields, forces, and charges is the same way you deal with gravity. Instead of a charge, you have a mass. Instead of gravity, you have an electric field. And instead of gravitational force, you have electric force. And we depict electric field by the letter E, and it's the field produced by source charge or charge distribution, independent of any test charge, like I mentioned earlier. Oh, that bullet point's not supposed to be there, but okay. And let's go over motion of charged particles really briefly. This is just a very brief overview. A charged particle in an electric field will experience force. And because it is experiencing force, the particle will accelerate according to Newton's law. Newton's second law. So that's just stating that if there's force on a particle, the particle will accelerate. We already know F is equal to ma, and we can just equate F is equal to QE, which is the force. F is equal to QE. This equation right here is representative of the force created by an electric field. Is a force acting on a point charge in an electric field, or a test charge in an electric field. And we can also equate that to mass times acceleration, because we already know F equals to ma. So the acceleration of positive charges is in the direction of the electric field. So for example, if it's a negative charge and all of the electric field lines are converging inwards, if a positive charge is placed into that field, the positive charge will experience acceleration towards the negative particle. Now, if the original point charge was positive and your test particle was also positive, it would move away because the electric field lines are oriented outwards. So the electric field lines of point charges radiate in all directions. Like I said, they essentially like it's radiating field lines in all the directions. And in 3 dimensions, while it's a little bit harder to visualize, the distribution is spherical. Now, when you're dealing with this on a test, or if it's part of your homework, it's normally going to be depicted as a 2-dimensional charge. So it's important to keep as a 2-dimensional electric field, but it's important to keep in mind that it is actually a 3-dimensional electric field. And like I said earlier, the electric field lines are directed away from the positive source charge and towards the negative source charge. So we just went over this a minute ago, so I'm not going to go over that. And drawing electric field lines is critical. So you need to make sure you draw electric field lines in the correct manner, that they're oriented correctly, that your arrows on the electric field lines are in the right direction. So the important thing with electric field lines is that lines must begin on a positive charge and terminate on a negative charge. So if this is a positive charge right here and this is a negative charge, the electric field line must start here and end here. That's basically what it's saying. And the number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. So if I'm drawing, say, 4 electric field lines for a point charge that has a charge of 2q, I'd have to draw 8 when it has a charge of 4q. So essentially what it's saying is it's proportional to the magnitude of electric field. The higher the magnitude, the more the field lines. And in the case of an excess of one type of charge, some lines will begin or end infinitely far away. Now, this is just saying that if there is more than one charge, the lines can technically go an infinite distance. Now, obviously, this won't affect you while drawing or reading, because you're not going to draw infinite lines. You're just going to draw like a couple inches worth of lines. So just make sure that it's clear that the lines haven't ended at the end point. You gotta ensure that you're depicting that they're not ending there. And this is very important. 2 electric field lines can never cross. Now, this is true in reality as well. Electric field lines do not cross at any point of time. So it's important to make sure that even in your drawings, they don't cross. And keep in mind, field lines aren't material objects. They're pictorial representations used to qualitatively describe the electric field. So electric field lines are basically the same way you draw gravitational lines. They're there, but they're not material objects. It's not something that is physically present. It's just a pictorial representation to help you get a better understanding of what's actually going on. So that's it for the workshop. So we went over electric charge, where we reviewed classifications of materials and properties of electric charge. Electric fields, where we reviewed properties of electric fields and the quantization of charges. And electric forces, where we reviewed properties of electric force. So